Okay children, now the question is, a particle A having charge Q and mass M is placed at the bottom of a smooth inclined plane of inclination theta. Where should a block B having same charge Q, same charge and mass be placed on the inclined plane so that it may remain in equilibrium? Okay, right? So what they have told you? They have told you that there is an inclined plane. So let this be my inclined plane. Okay, right? This is my inclined plane. Okay, right? So a particle A having charge Q and mass M is placed at the bottom of a smooth inclined plane of inclination theta, right? So this angle is theta, and this is the point where I have kept the particle A, right, of charge Q and mass M. Okay, where should a block B having same charge and mass, right? So the block B is going to have the same charge and the same mass, children, right? Mass be placed on the inclined plane. So I am going to place the block B on the inclined plane so that the block remains in equilibrium. Okay, right? So in order for the block to be in equilibrium, you know that they both must be repelling each other. Okay, right? So they have asked you to find at what point should I place the block in order to maintain it in equilibrium. That is, it shouldn't fall down. Okay, it shouldn't slide down. It should be remaining in that position itself, right? So let that distance from the particle to the point where the mass has to be placed so that it remains in equilibrium be D. Okay children, right? So the block is in equilibrium. So under equilibrium, let's see what are the different forces acting on the block. Okay children, right? So the first one will be our weight mg acting in the downward direction. Okay, right? So for the block, you know that this will be the normal, right? So this is making an angle theta. Am I right? So as this is making an angle theta, you know that mg has to be resolved into mg cos theta along the reference line and your mg sin theta perpendicular to your cos theta component. Mg sin theta acting along this direction. Okay, so this particle A and the mass M and the block B are having the same charge. Am I right? So as they are having the same charge, this particle A will be repelling the block along this direction. So this is going to be the direction of the Coulomb's force of repulsion. Okay, right? And this is the normal reactional force, right? Normal reaction force due to the weight mg. Okay children, right? So now this is under equilibrium, right? So as this is under equilibrium, I can say that this mg cos theta is being balanced by the reactional force, normal reactional force, and the Coulomb's force of repulsion is being balanced by mg sin theta. Okay children, right? So now let us see. Now this electrostatic force of repulsion is being balanced by your mg sin theta, right? What is the expression for the Coulomb's electrostatic force of repulsion, children? That we know that 1 by 4 pi epsilon naught, right? Coulomb's law, 1 by 4 pi epsilon naught. Charge is the same, so it is going to be q square divided by the distance between the two charges is d, no? So this is going to be d square is equal to mg sin theta, right? So from this, what will be d square is equal to, d square will be equal to, right, 4 pi epsilon naught will be going up, or else let us take this d square there and mg sin theta to the downward, right? So what will I be getting, children? Q square, the whole divided by 4 pi epsilon naught. Mg sin theta comes downward to the denominator. So mg sin theta. So what will be d is equal to, d will be equal to square root of, right? So square root of q square will be q again. So q, I can take it outside, root of 1 divided by 4 pi epsilon naught mg sin theta, right? So this is the distance at which I should place the block B in order for it to remain under equilibrium, right? In order it to be there without sliding down towards the particle A. Okay children, right? Hope you have understood. If you have any doubt, you can ask me in the comment section.